Hello, I hope you had a good opportunity to discuss this part of a poem written by Samuel Taylor Coleridge, The Rime of the Ancient Mariner, water, water everywhere, not a drop to drink, and came up with some sort of understanding of that with the people at your table. I mean, obviously, the key word is salt, okay? All right, so we're going to be, this is our first actual unit. The textbook will be posted online and eventually on Google Classroom at the very top of the week 1, week 2, week 3, week 4 for this quarter. The textbook units will be posted up there so that you always have them to reference while you're elsewhere, okay? And this is our first unit, our first marine science actual unit from the curriculum, okay? So this is the format. You'll see that the slides, slide numbers are down here. That one's hard to see, but oftentimes they're easier. That's a number 2, so we're on slide 2. You can also look over here, slide 2. And on your notes, it says slide 2. And sometimes there are questions embedded inside your notes. So just be aware of that. You should be kind of used to this by now. We've already had sort of two sections of notes already. And this one's actually going to be in 2 parts also. We'll do the next part on Monday next week, okay? So you fill in the blanks, you read it, you fill in the blanks, and of course, if you have any questions, that guy will pause the video and you can ask him, okay? So, the changes of state in water. Now, a lot of this is going to be review, right, from physical science or biology class. So, between solid, liquid, and gas in terms of kinetic particle theory. You're also going to learn about this in chemistry class. So, again, these basic parts are redundant amongst the different areas of science. So, obviously, we know solids are going to be, we learned about, well, you should have learned about that in biology if you took biology, but they are the least dense form of water. Everything else is more dense when it's in a solid form. But because water makes this special pattern called a triad, a crystalline lattice structure, it is less dense than the water state and the vapor state or the gas state, okay? But the kinetic energy is very similar to every other substance, like the faucet that's at your table right now. That's in the solid state. And if I were to melt it, it would be more easily flowing and have a higher kinetic energy. And then if I were to boil the metal, and metals can boil at hot enough temperature, everything has a boiling point, that would be the most kinetic energy, moving the fastest, okay? So least kinetic energy, movement. Kinetic energy is the energy of movement, right? Middle in liquid and gas is the most movement, so the most kinetic energy, okay? And temperature is the measure of that kinetic energy. So when you measure something's temperature, you're measuring how fast the particles are moving and hitting that thermometer sensor. And then evaporation occurs at the surface of a liquid. The more kinetic energy it has, the more evaporation there will be. Structure of an atom. So again, the basics of water, we need to understand this. So we know that atoms have a nucleus that have protons and electrons. The protons are positive, and neutrons. So the word electron there, I just read it. The neutrons and the protons are in the nucleus. So, and the neutrons don't have a charge. They're neutral, neutron, protons, so it's the P positive, and then outside of that would be the electrons. And they orbit like a moon around a planet or planets around a star. And the examples here are the lithium atom and the carbon atom. The orbits are also called shells. And I think you had to label that Yeah, you had to label that on the bottom of your page. So hopefully you had time to do that. If not, remember, if you don't have time for one of these, just skip it, go too fast. You can always look at a neighbor's later, or you can go back, because these are on YouTube, so these videos. And the link is on Google Classroom. So, understanding seawater is a mixture of different elements and compounds. We know that seawater is not fresh water. I think most of us here have been at the beach at one time in our lives and have tasted seawater. So it's salty, okay? Simply put, saltiness is called salinity. And it's how many solids and gases are dissolved in the water, okay? Salinity. Saline, salt. And there are different kinds of salts, not just sodium chloride, which is table salt, which is what you're familiar with. So you have to fill out that chart on your notes that has the major components of seawater. And you will see that calcium, magnesium, sodium, potassium, chlorine, okay? Sulfate actually is more than potassium. So this is not in any particular order, but you can take the biggest numbers and you see them here. Chlorine, sodium, sulfur, and magnesium are the four biggest ones. And there's a lot of others. And you can see difference between ocean water and river water, which is fresh water, right? For the most part. I mean, it's not pure fresh water. It's got still some dissolved nutrients, not nutrients, but dissolved chemicals from the land, right? Washing into the river, and then the river deposits it in the ocean, and the ocean gets all of it, so that's why the ocean is saltier or has a higher salinity than the river water, okay? And you can see the numbers are much higher in the ocean water than they are in river water. Slide 5, describing using diagrams. So these are, as I'm just it's kind of obvious I thought, but maybe I need to explain. These are the different sub-parts of the unit that are part of the curriculum that you have to know for Cambridge. That Cambridge wants you to know before earning your credit for this class, okay? And earning the credit for this class means you have to pass the AICE papers in the spring. So, and these are the points. So each one is listed and on your notes with the information you need to know below it to understand that topic, okay? So covalent bonding. Water is held together, one molecule is held together by what we call covalent bonds. The covalent bonds are shared bonds, bonds that share electrons. So the H2O, right? The H's, the hydrogens, are sharing their individual electron with oxygen's electron to make a complete bond. And that's called a covalent bond. In this scenario. Sodium chloride is different. We'll get to that in a minute. That's an ionic bond. Again, these are words you've heard in physical science or biology. All right, so you have to be able to look at a chemical formula like these. These are all different kinds, circle ones, like 3D ones, linear ones, or hand-drawn ones. You have to be able to look at that and understand covalent molecules, if they're covalent or otherwise, okay? And so you're going to label these, I believe, in your notes. So here is obviously water, H2O, carbon dioxide, 2 oxygens, and you can see how many shared electrons are in that molecule. This is oxygen, the air, in the air you breathe. This is the oxygen that's in the air you breathe. It's 2 single oxygens bonded together by a covalent bond, okay? And those are shared. Glucose is the sugar that plants make, that we eat. Sulfur dioxide, this is given out by volcanism, volcanoes underwater, and we're going to talk about that in the future. And then this is a long chemical. I don't know, hold on a minute. I'm not sure what that is. It's some sort of alcohol, because it has an OH on the end of it. So I know that it's an alcohol, but I'm not sure what exactly. So anyway, you can see that the covalent bonds are circled, and that means that they're shared. Okay? Oh, it's glucose. Is that also glucose? I think that's also glucose. Yes, it is. Except it's opened up now. Okay, so these are the same. Drawn differently. Now, slide 7. Again, using diagrams, now we're talking about ionic bonding. Ionic bonding is rather different than covalent bonding. It still has to do with electrons, and it still has to do with 2 or more atoms being bonded together, but in this case, it's not sharing. It's a giving and a taking, okay? It's a giving and a taking of electrons between the two. So, or a loss and a gain. Loss and gain. And if you're losing an electron, because electrons are negative, right? You're going to become more positive. And if you're gaining an electron, electrons are negative, you're going to become more negative. So in the case of sodium and chlorine, to make sodium chloride, which is salt, the salt you use for your French fries, okay? Or in your soup or whatever, this is how they form their bond. So sodium has this extra electron, and chlorine has 2, 4, 6, 7. It wants one more to have 8 to be stable. You put them together, and sodium loses this electron and gives it to chlorine. So it becomes positive, and that becomes negative. That is an ionic bond. That's the basis of an ionic bond. And this stuff here, sodium chloride, you sprinkle on your French fries. But sodium is a metal that looks like silver, but it's very soft, like butter. You can cut it with a butter knife or your fingernail. And if you put it in water, it explodes. Like if I had a piece the size of my finger and I threw it in that sink in front of you that was full of water, everyone around the table would die or become very badly injured. Chlorine is a deadly green gas. 2 breaths and your lungs stop working. Put them together and you get something you sprinkle on your French fries. That's one of those miracles of science that is just so amazing. All right, slide 8. Identify, including using diagrams again. So you'd have to be able to either see the formula or a diagram like this to be able to determine if something is ionic, okay? So in this case, we've got sodium chloride, which is this, okay? One of the major salts in the ocean. And we've got calcium carbonate, which is another major salt in the ocean. A salt just means that it's got a cation, a positive, and an anion, a negative, and they've come together to form an ionic bond, okay? So you can see here that they're stacked in neat rows and columns when they combine. This is like a crystal of salt that comes out of your salt shaker. That's what this is, but expanded in so much that you can see the individual atoms in the salt and how they're stacked up evenly. And if you see these charges give away, anything with a charge gives away ionic substances. If there's no charge present, it's not ionic, it's covalent. Unless you're talking about polarity, but that's different. We'll talk about that later. Okay, so just by looking at the chemical formula, you should be able to state what these substances are, okay? So sodium chloride, magnesium sulfate, calcium carbonate. You have to know the word. Yep, if you see this word, you have to know how to write that symbol. If you see the symbol, you have to know how to write that word. Does that make sense? Okay. State the chemical name and formula of salts found in water, in ocean water. This is what magnesium sulfate looks like. It's also called Epsom salt. It looks like sodium chloride, but you can't eat that. You would die. Sodium chloride you can eat, but you can't eat a lot of it, right? Because it's bad for you. It's only supposed to be used moderately, right? And then calcium carbonate looks like this. It's essentially powdered shells from the ocean, because that's what the shells are made out of, calcium carbonate. And here's some salt on the side of the Dead Sea. Or actually, that could be the Great Salt Lake in Utah. I don't know. Anyway, either way, you're going to find huge salt deposits like that on the side of the ocean, side of the water. And so the next question there, slide 10, is marine sources of calcium carbonate. So you have to know, so all these organisms pull in calcium carbonate from the water to make their bodies, right? But when we collect calcium carbonate for use on land as a natural resource, shells, well, we don't hurt corals anymore. They're endangered, right? So oyster shells and clam shells, fish bones, when fish are collected for food, the bones are converted also and used. Red seaweed has, you can find this kind of seaweed down in the Keys. And crustacean shells like shrimp or crabs or lobsters. All right, slide 11. We only have 4 slides to go and then we're done with this first part, okay? The formation of hydrogen bonds in water. So water is sticky, right? It's sticky because it's a polar molecule. Now the individual atoms themselves don't have charges, but the molecule has a charge of a polar nature. One side is a little more positive, that would be the 2 H's, and one side, because oxygen is so electronegative, it's a little more negative. And because of that, they attract and repel each other depending upon whether it's positives or negatives. They repel, right? Because likes repel and opposites attract, okay? So the opposites, the negative part of the water molecule and the positive part of the water molecule are going to form this bond called a hydrogen bond. It's not a covalent bond. A lot of students mix up these two bonds. The covalent bonds are much stronger and they hold the water molecule together. You can't take water and karate chop a bucket of water and break water molecules apart. You can't do that. You need to add like electricity or something to it. It's called electrolysis. And you can do it right here in the classroom and make hydrogen gas and oxygen gas. But we're not talking about that. We're talking about the bonds that hold one water molecule next to another water molecule. I could take water from a cup and pour it into another cup and have half the water in this cup and half the water in this cup, and that's the hydrogen. I separated hydrogen bonds with gravity. I didn't separate the covalent bonds. Does that make sense? I hope that makes sense. Okay. So water, that makes water sticky. If I threw water on you, it would stick to you. If I threw water to the wall, it would stick to the wall. If I touched water to water, they would stick to each other because of this little magnetic attraction they have. And when they use these hydrogen bonds to form ice as well. But the ice is more spread out than liquid, because the liquid has more energy and it can move around. The ice has less energy, so it can't move around. So it's locked in place. And they get locked in place because of these hydrogen bonds to be less dense. They're more spread apart. That's why ice floats. Ice floats, doesn't sink. If it sank, all the creatures in the ocean would die. The whole ocean would freeze from the bottom up. Lakes would freeze from the bottom up, right? And all the fish would be frozen dead. So here's just 2 ways to visualize it, all right? And here's covalent bonding, these blue arrows, versus hydrogen bonding. So we're zooming out now, and we're including 5 different water molecules instead of just 1, and the hydrogen bonds occur between the hydrogen and the oxygen. Hydrogen, oxygen, hydrogen, oxygen, hydrogen, oxygen, okay? Makes water sticky. It's almost like you see when you take a balloon and you rub it on your hair and then you stick it to the wall. It's kind of like that It's kind of like that. Imagine the balloon is, one of these, and then the wall is one of those, and stick together. All right. Lots of information here on slide 13. So hydrogen bonding affects properties of water. We talked about its stickiness already. It's polarity, right? So that's one of them here. Number 8, you're supposed to list 4 of these. The numbers are given to you in those spaces on this slide. And then there's lots of information that comes afterwards. So it's limited solvent action, and that essentially means it's the universal solvent. That's number 10. Density, that's anyway, that's number 1. Specific heat capacity, that was number 3, and one more, I forget. Anyway, so water is called the universal solvent, but that's because it dissolves a lot of things. It doesn't dissolve everything. I mean, even metals dissolve in water, but fats and oils won't. You know that when you're making a salad dressing, that the oil floats to the top and you have to shake it up, right, before you put it on your salad. So that is one limitation, but really they dissolve lots of different things, lots of different substances. And that's why you're able to digest your food so well and get the tiny particles into your cells, because you're mostly water. Carbon dioxide is about 200 times more soluble than water because of being more polar than water. And we'll talk more about that. Temperature, and this is just introduction, okay? Solubility decreases as temperature increases. So if I heat the water, gases leave. Solubility will decrease. But if I heat the water, I can put more solids in. It's reversed. So inverse, okay? Density is mass divided by volume. We'll talk more about that. For water, lower temperatures increase the density until it freezes. So really cold water, right before the freezing point, will be at its densest state. And then when that crystalline structure forms of ice, it becomes less dense than liquid. And also, if you increase the salinity, if I add salt to the water, it will increase the density. Why? Because there's more stuff. More stuff, more dense. And when water freezes, it actually pushes the salt out. The salt won't fit in between the crystal lattice because of the hydrogen bonding, and kicks the salt out. So any ice in the ocean is fresh water. It's not salt water. That's why they've talked about taking icebergs and towing them to the desert and using that water for, instead of just letting it melt into the ocean, using it to irrigate crops and things like that, or to fill reservoirs for drinking water. And then something called specific heat capacity. Water has a very high tolerance to change in temperature. So if I were to put a pot on the stove and heat it up with water in it, right? And I came back a minute later, and if I touched the pot, I'd probably burn my finger, right? But if I touched the water, it would just be warm. It wouldn't burn my finger yet. It's only been a minute. Because it takes a lot more heat to make the temperature of water go up. High heat capacity. All right, slide 14, almost done. One more slide after this. These are just some vocabulary about solutions that you should have learned in physical science or biology. Definitely chemistry. If you take chemistry, you'll be learning these again. So, the solute is the thing that goes in the water to become a solution. So an example would be salt. Sodium chloride would be an example of a solute, okay? The solvent is the water in most cases, the universal solvent. That is going to dissolve the solute. The solution is the product that is made when the solute and solvent come together. It's a solution. It's like a solution to a math problem. It's when this and this gives us this, a solution, okay? And then solubility is the ability. Solubility, ability, oh my gosh, it's like the same word, of a substance to dissolve. So if something has good solubility, it will dissolve well. If something has poor solubility, it will dissolve not well or poorly, okay? So sand. Sand has poor solubility. Why? Because it's rocks and shells. And so they don't dissolve very well in water. And that's a good thing because the whole earth would be water and all the rocks would be gone, right? But salt does. Salt does dissolve well. And these are all just examples of solutions. It's just colored water in that case. All right, and our last slide, see the stop sign on your notes. Describe how soluble salts like sodium chloride dissolve in water by the dissolution of ions. So you have to explain in your notes what's happening in this diagram. So I will explain it up here. So, you have water in a container, in a beaker, whatever, a glass, and you pour the salt in. And what does it do? It makes a little pile at the bottom of the container. And if you wanted to dissolve it, you got to stir it up or shake it or heat it, whatever. You got to stir it up, right? But you could also just leave it there. And you'd come back in so many hours and it would be gone. Well, not gone. It would be dissolved in water, okay? It's called dissolution. So, the sodium ion is surrounded by water molecules as it's sitting there on that pile. Water molecules surround it. Check it out. Sodium is positive. Remember the ionic bonding we talked about earlier? Because it loses an electron, so it becomes more positive. So what part of the water molecule is going to surround the sodium? The negative part. Because water's polar, so it's got a positive and a negative side. So the oxygens are going to surround that sodium particle. Oppositely, the chlorine is negative because it gets an electron, right? It's an ionic bonded substance. So the positive side of the water molecule is going to be attracted to the negative chlorine atom and surround it. All right. That's what it says over here. And then it's going to pull them apart into the water, making them dissolve, making them disappear, right? Okay? So, but they don't really disappear, do they? They're just floating around in the water. And you know that they're still there because if you were to drink that water 24 hours later after all this has happened, you would be like, right? You'd spit it out and say, or maybe you're using it to clean your mouth and rinse your mouth out, because sometimes when you get dental work or have a canker sore in your mouth, you rinse with hot salt water, as hot as you can stand it, and that will kill bacteria. So bacteria don't typically like salt water. But you don't drink it, because if you drank just a cup of seawater, you would probably throw up. Hence our bell work for today. Water everywhere, but none to drink. You would not be able to hold it down. Your body would be like, this is too much salt, and throw it up again, okay? So this is dissolution of ions, dissolution. And it's a form of the word dissolve, dissolution. So that's how it works. It's rather simple, actually. Now you can make it go faster by agitating it, shaking it, stirring it, or even heating it up, because you're making the kinetic energy of the particles go faster and bounce around, and they can find the other particles faster, okay? So that's the first part of our notes. That guy over there will tell you what to do next.